Perfect. It's time to start. Thank you everybody for coming. So many of you I didn't expect at lunchtime. How are the sandwiches? Okay. So I guess most of you are using IntelliJ, right? Clap. Yeah, perfect. So my name is Anton. I work at JetBrains as a developer advocate, actually in Kotlin team, but people like when I do demos. So here I am, and I'm going to do a little showcase for you about the debugger features in IntelliJ. It covers most of the features about the behavior, like breakpoints, stepping, and everything. I will show you quite a few tips and tricks. I hope some of them will be useful for you at work. You don't have to memorize everything. But I will not touch the memory debugging. That's a separate topic of its own. And first of all, I want to philosophize a little bit why debugging, because it's not a very productive thing to do. You should rather be writing tests and write the correct code, then you don't have to debug. But once you're already faced with a problem, like something is broken or you don't really understand how it works, then you should be diving into debugging. You kind of don't have any other choice. And then it's good to have some, productivity features in that area or some tips and tricks to improve your workflow, to make yourself more efficient. And in fact, I want to start with a feature which is not really a debugger feature, but the debugger itself is an interface to that feature. Have you heard of hot swap? It has been in Java for ages, since Java 1.4. It's kind of a combination. Usually it's used in combination with the debugger, although you can use it outside of the debugger as well, via some agent or via the serviceability features in the JVM. And I want to show you a little demo first. Let's look at the code. We have a loop, an infinite loop that just assembles a string using the string builder, and sometimes it reads something from the standard input. So let's start the debugger and see what happens. Right. So we started the application. It doesn't print anything yet, and we don't really know. We don't see the stack trace. No frames are available. And what we can do at this point is to ask the program to pause with this little pause button. Everybody can see it. So if we pause there, we'll see that it waits for an input, right? We have this read line statement there, and we can traverse back through this stack trace right here and see, really we are waiting for the next line, and it was called from this method. Kind of a neat feature to inspect the state of your application and so on. So there we can start thinking and reasoning about our application's behavior and maybe experiment with it a little bit. And to proceed further, maybe I don't want to read the input all the time, and maybe I would like to change this method behavior, but restarting the JVM all the time might be tedious, or maybe slow in some cases. Maybe you just want to experiment on the spot, change the behavior for once and roll it back and keep the application running. Then hot swap is kind of a tool for that. It's limited to the statements, to the individual statements. You cannot add new methods, implement new interfaces, but still it's pretty nice thing to do. But let's see what we can do here. We stop at breakpoint, and it waits for an input, so let's do hello. And we should let the program actually go. Now it's at the breakpoint, right? So it's waiting, and probably we don't want to input anything from the standard input all the time. Let's just return an empty string, recompile the class, and the IDE will ask you if you want to reload new classes. Basically, it watches the output folder for the compiler and sees that the timestamp of the class has changed and there are new bytes, so it can push the new bytes through the JVM. But it doesn't do any validation at that point if you change the schema of the class or not. Those are just the new bytes. And if there are incompatible changes, the JVM will just say that the hot swap failed and so on. But currently, we just changed a single statement. It reloads actually 2 classes because in my file I have 2 classes. And only one of them actually has the changes. And now if we let the program run to the next and remove the breakpoint, let it just run, we'll see that it prints out the statements. We can modify the result a little bit more, like this, like recompile and reload again. We can see it running. Well, it's fun. You can kind of improve your workflow, debugging workflow, when you need to experiment a little bit, but we can do some changes without actually changing the code. So, for instance, we can manipulate the state when we are in the loop. Let's see, we have the loop variable I, right? It's displayed as a hint right now, but we can modify this state through that hint as well. Set value, set to 0, for instance, and we kind of restart the loop. Just a fun thing to do. Loop forever when needed. Or we can modify the contents of the string builder. For instance, we can just reinitialize it, like new string builder. Boom, we have an empty string. Or we can actually force the return value and say that we want to do a force return, and the value should be something like debugs forever. Done, and it will print debugs forever right here. Good. Or let's do another experiment or another change without changing the code. We can actually, whenever you see the stack trace right here, but when you hover on those frames, let's actually stop right here to have more frames. So our stack trace consists of main method, get value method, and then the read method. And we are at the read method, and we kind of want to return back. Right? So when you hover on those frames, you can see a little arrow, a little back arrow, which says that's reset frame. So it's actually rolling back the stack. I'm jumping out, but not forward. Right? So it drops the frame. You can start over, but the state, if you have any state in that class, it remains unchanged. So you have to account for that. So you can roll back the behavior. You cannot roll back the state. If you need to change the state, you have to kind of manually do that. And another interesting thing is you can actually force return, but with an exception. Sometimes it's useful to experiment how your application behaves in some situation. If some library throws an exception, but you cannot kind of easily create this situation, and you can just force throwing an exception, something like new IO exception. This is a bug. Okay, obviously my application should crash. There's a uncode exception handler set by the debugger for this specific situation, and it stops here automatically. We don't need that. We can just let the application go, and the application crashes, and we can see the exception, right? And have you been at the keynote? Have you seen the assistant, right? Yeah, perfect. The one thing we didn't show there is the explanation for the exceptions. So there's a little feature, a little button appearing on the right-hand side that you can click, and the assistant will explain you what the error is and how to handle that. Kind of a convenience feature. Nice. Okay, let me do a check. is there anyone who learned something already? Not a time wasted, right? Especially at the lunchtime. Perfect. Let's proceed and see what else we can do. So we did some very basic manipulations with the code to experiment with the behavior. Now, who remembers when Java Lambdas appeared in Java? When? Java 8, right? So since Java 8, we started writing those nice expressions in one line with streams, right? And then we suddenly realized that we better break them down into the separate lines because it's not possible to set the breakpoints for every lambda separately. In fact, in IntelliJ, you can do that when you click on the line like this, when you have a stream expression with different lambdas and so on. When you click on the left-hand side, sorry. Okay. When I need it, it doesn't show up. Anyways, we just skip it. But if you have a full line there and you run a debugger, yep, and you want to step through that chain. When you do a step into, it's actually called smart because it will evaluate the expressions on that line and ask you where do you want to jump. So I do a step. I'm not sure if the highlights are visible. Let me zoom in. Maybe it's possible to. You see the highlight or the? So it's kind of a little bit different color, right? So if we I click enter, I jump exactly to that specific location in the Lambda, and then I can inspect exactly that step, right? This is nice for kind of if you want to make sense what the stream is doing and how the logic is actually implemented for this pipeline, but it's not very productive to jump with the step intos and step overs over this kind of chains. We have a slightly better way of doing this with trace current stream chain action. So when you're at breakpoint on a stream, you can call this action. It will evaluate the whole line and check what are the operations and how they transform. And if you flat it, you will see what's the flow. Is it something you just learned about? Okay, perfect. My job here is done. Thank you very much. Okay, that's a nice feature. I hope you can experiment with that and see. It works for Java stream chains and for Kotlin sequences as well. Right, let's stop the debugger and proceed further. We have method breakpoints. So method breakpoints, usually if you think about breakpoints, you think about a line, right? So you want to set a breakpoint on a line. Actually, you can set breakpoint on a method, and historically, people avoid using them. If they even know that it's possible, they avoid using them because it slows down the JVM very much. In IntelliJ, because of this problem, because of slowness, the method breakpoints are emulated by default. So when you set a breakpoint on a method, it will actually set the breakpoint on the first line. But for you, the whole UI, the whole thing does not change. So it behaves as if it's a method breakpoint, but it's faster then. So the emulation makes it faster. But when is it useful at all? So for instance, we can set a breakpoint on an interface method, which doesn't, we don't have an implementation right here. We just say that I want to catch all the invocations for the implementations of that interface, right? For that method. And it behaves like a wildcard for all the types that implement that interface. So if we run, or debug, run the debugger, we will stop on the implementation. You see, we have boo, we have some kind of statement here, and it implements the base interface, and that's nice, but it's not very impressive, because in practice, if I just set a breakpoint right here, because I know where it's used, right? I can find usages, and just run the debugger again, and do step into. The debugger will ask, where do I want to go, into the print line statement or into the boo method, and I will end up in the same place. So basically the same process, and I get the same result, but just with a bit more steps, not too many actually. But where it is impressive or useful is when you don't have any usages. Like it appears the static analysis, the IDE doesn't show you that there are usages for that interface, but you clearly see that there is a behavior in the application that is implemented by that method. So how come? So like the IDE tells me that it's unused, right? But let's experiment and say I want, like in my main application, I don't see that method being called at all. All right, let's debug and see what is happening. Boom, and we stop at the foo method. So why? Because that foo method was invoked through the reflection. And why didn't the IDE catch it? Because like it could be smart enough if I just type foo there as a string, the IDE will actually find the usages. So if you run find usages, it will detect that there is a constant that is used as a method invocation for that specific type. It will show you that there is a usage of that method, but we can concatenate the string and kind of trick the static analysis of the IDE, and the IDE will not show you that there is a usage of this method. So another trick for you to catch some nasty invocations. All right, let's stop that. Method breakpoints allow you to catch any invocations. Let's do a bit more with breakpoints. That's a fun thing to do. Well, when we talk about breakpoints, we just, we already know that there is a line breakpoint and there is a method breakpoint. The icon is slightly different, right? But there are options. You can configure the breakpoint. So if you do a right click on the breakpoint, you get a few options, and if you go further, there is a lot of them. And well, it might be quite complicated on the first sight. So let me show you a few tricks what you can do with those options without actually diving into those menus. We have an application that we're gonna run without the debugger first, and it just creates a cache instance which is a singleton, very naive one, and we print out the object reference, and we'll see that this object reference is always the same as it should be, right? We have only one instantiation of this cache as it should be. The reference number, is always the same. What if we want to experiment with this behavior and we need to reinitialize the cache always during the implementation? One possible situation is to stop, or one possible way is to stop at this breakpoint and every time manipulate the state, set the instance to null. But in fact, we can automate this. Currently, I do shift and I select. I do shift click. You see the breakpoint is now yellow because it's configured as a non-suspending breakpoint. It will not stop at that breakpoint. It will just do something with whatever I ask it to do, like through the configurations. And currently there is, since I selected the value in the editor, it automatically set this value into the evaluate and log field right here. I can set it to null, for instance, right? Every time. And when I run in a debugger, I will see that the reference is different every time. So this breakpoint behaves like automation for my debugging process. In fact, you can do more with them. The fact that the line hits at the breakpoint is recorded. So when we want to evaluate some complex workflow, let's say your application receives a parameter, and then you pass on this parameter further and further and further, and you try to make sense how this value is spread across the application. And when you reach out the very last call, you don't remember how you actually got there. One of the things that you can do here in the IDE is actually analyze it with data flow analysis, like data flow to here. How did I get here? Analyze and get the whole chain of invocations back into the first call, or like vice versa. You can do it, from this place as well, like something like data flow from here. Okay, so we see there is a branching in this method and so on. What we can do with the breakpoints here is that, for instance, the first branch that we have in the execution is very noisy, and I'm interested in the other use case. When the other branch is executed, I want to hit that other breakpoint that I set at the very last position, for instance, right here. So I want to stop here only if it's invoked through the step 4 in my application, right here, right? So what we can do here is set the breakpoint, configure it as a non-suspending breakpoint. So we just record the fact that we're now hitting this method. And in the other breakpoint, we can say that I want to disable it until it hits line 249. And it will be disabled. You will see the icon that it's not filled, right? It's disabled. And once we run the application, or actually debug it, boom, it stops at the breakpoint, but let's inspect the stack trace. It comes from step 4. So we skipped all the invocations that were on the other branch, and now we only stop there when we have a certain condition or certain breakpoint that hits, on the way here. The data flow that I showed you previously is not actually a debugger feature, it's a static analysis feature from the IDE, right? But static analysis can kick in the debugger as well, because in the debugger we have the real values in the variables, and we can start evaluating some of the things. When we get here, you will see that the debugger evaluates the expressions on the go, and it will immediately tell you that, well, the ID is not null, right? So you will never hit this branch. And it's very useful when you start debugging like logic with some specific values, and you don't know why some customer with ID whatever doesn't get some orders, and you start debugging this logic, and you will see that debugger, hey, it shows you the whole block that is not executed as gray. You actually see everything as gray here, but at least it's underlined. All right. So it's kind of a combination of debugger features and static analysis right in the debugging session. All right. Let's do a bit more complicated example. Tests are like, do you like debugging tests? Especially with concurrency. Let me explain you the code, the use case. We have two threads, the main thread and the other custom one, where we try adding the same number, 17, only if it's absent, from the two threads. If I run this test, the test will pass, hopefully. Yep, it passes, it's green, we are good, we ship to production, and then eventually in 1 month we have a bug. What we can do here first is to, because it's a concurrency bug, right? It might happen and it might not happen. We may run this test many, many times and they all pass. And maybe on some invocation 250 it will fail. So how do you catch this kind of things? Without debugger, we can actually configure the test to run many times, as many as you wish. There is a repeat option, and currently it's set to once, but we can say until failure, and we may wait for a long time. But let's try that. Sometimes it just fails. If we, yeah, done. It actually passed 170 times, right, and failed eventually. Sometimes I had to wait for 1,000 invocations, sometimes for 10,000, but sometimes it just does not finish. It always passes, so you don't know. Let's see what we can do in the debugger to emulate this situation and inspect how the code behaves. So we want to catch the situation when both threads are adding something into the list. And if we set the breakpoint as is, it actually stops all the threads. But if we go into the options, we have this suspend checkbox has two options: to stop all the threads or only the thread that hits the breakpoint. So if we set only the thread one, we will see a little bit different behavior in the debugger. Let me debug the test. And we will see a notification that it actually stops first, right? And then we have a notification that there is another thread that also hit the breakpoint. So we have two threads at the breakpoint right now, and we can switch between them and inspect what is happening in there, like separately, and step in there separately. And we have two threads, both at the breakpoint, this main thread and thread 1, right? So what we can do here and how we can see like what is happening. So we are in the thread 1 and we are checking if the list contains value x, 17. Okay, it doesn't. Nice. Let's go back to the main thread. It doesn't contain the value as well because we didn't add it in the previous thread, right? So the condition will evaluate to true, and we get to the same expression, to the same statement for adding the x, and now we do the step forward, and the list contains a value, and we go back to the other thread, right? Was it the main thread? Yeah. And it's there. We add it again, so we have two values there. And the test crashes from the first time, right? So we, using this configurations for this breakpoint, we were able to validate the behavior and really confirm that there is a bug in the code. We're not going to fix it, it's just the synchronization, so we need to add synchronization to this method to see that it's fixed. Then the option to run it continuously will not help us, it will always pass. Okay, perfect. So we had this instance, cache and everything, concurrency. Finally, we reached to the renderers. In fact, let me go back to the example with the streams to show you one thing that I did not show that is related to renderers. When I showed you the stream trace debugging, right? The values that you see in this kind of views and in the watches view in the debugger, they are like displayed as strings usually. So you basically need to have a good toString method, or it should be a primitive, or if it's a complicated object, some custom one, you need to, let me switch the view. You need to have a renderer. And renderers are kind of, configurations that you can configure yourself for the complex objects. For instance, if it has a lot of nesting and you're interested only in some specific value in that object graph, and you want it to be displayed on the top level, then it's possible to create a custom renderer and get it applied. And view as is the place where you get to those renderers. Like you can create your own, or just use this toString method. So let's check. Currently, this user class does not have a string. toString method is kind of overridden with this expression. So by default, it uses my default kind of custom renderer to display values for this user. But it can get more complicated. For instance, maybe you want to render collections somehow differently. Maybe there is a lot of data to display, and we can do some other tricks with those renderers. So in this example, I run the debugger and just stop at the very last line. And you see we have like a list of integers right here, and the size is 200, so it's reasonably big already to display in the view. And I have created my own renderer for them specifically, which I will show you how it's created. First of all, it shows the first 100 elements only, right? But then the rest you need to ask for the rest. Please display them. Like you need to double click on this line right here, and then it displays the rest. So how is this implemented? It's good for heavy objects, or like collection with the heavy objects, for instance. So if we go to the view as, create a renderer, and you'll see in that view for this type, no, for this one, sorry. Interesting, I have this custom rendering working, but I don't see the expressions. Let me check again. Customize data views, maybe, no. I lost it. Okay, that happens to me sometimes, sorry. So you can create a list of expressions like this, like please, like list, or this, and then no, maybe I want to take 100 and do toArray, because the debug views work with arrays, not with the collections. And then on the other line, on the other expression, I would do skip 100 and then take the rest and display as array. So I will have like a separation of those two slices in my view. So then to get the rest, I will have to double click on the collection to expand further. All right, so those are the renderers that you can configure through the views, but actually IntelliJ provides or works with its own annotations if you want to share those renderers to the team. So for instance, the student class, all right, we have this courses collection in this class, and then I want to display them somehow differently. Then I can use annotations in the code to help the debugger. So you're basically sharing the configuration through the annotations. Then I will have like a watch called name that displays the courses if the courses is not empty. that's kind of a way to share the configurations in a team specifically for those kind of objects. And it's useful when the object is really big and has a lot of nesting. So I think I have showed everything that I wanted. In fact, it's a little faster than I anticipated. If you have any questions to me regarding the debugging, maybe you can catch me at the booth today still. And thank you for coming. I hope you have a great conference, and I really hope you learn something that you can apply at your work. Thank you very much.